All right, so now we're going to talk about the infinite dimensional manifold of probability distributions. And the basic idea is that if you recall, when we talked about this space of discrete distributions, discrete probability distributions, it has both the structure of an exponential family and a mixture family. And there's a sense in which all possible distributions, which are discrete, embeds into this space. And so if you wanted a space of continuous random variables, we want an embedding space which plays a similar role, okay? And this is where it comes in, this infinite dimensional manifold of probability distributions, right? So on infinite dimensional manifold of probability distributions, so recall that the discrete probability distributions are both an exponential family and a mixture family. And sort of any statistical model of a discrete random variable embeds into the space of discrete probability distributions by definition, right? Embeds into this space. So the essence then is that we want something similar. It's like which plays a similar role for continuous random variables, right? So we want something analogous for statistical models of continuous random variables. Okay. And in particular, we want something where statistical models of continuous random variables can be embedded into some sort of ambient space of probability distributions. Okay. So, so to do this, we have to consider sort of an infinite dimensional function space. And you know, for the purposes of this discussion, we're not going to go too much into the weeds. It's like in terms of the functional analytic aspects of it. But you know, admittedly, one has to be careful. It's like when doing this, all right. But we're not going to take an extraordinarily rigorous perspective at this. So let's see how you can do this. So let's say that we have some p of x be a probability density function of a real random variable. real random variable, which we denote by x. It's like in the reals. Okay, which is mutually absolutely continuous with respect to Lebesgue measure. Okay. And sometimes it's like it may be better to write the probability density function in terms of a different measure, for example, Gaussian measure. Okay. Yeah, but it's like, but for now, it's like let's just consider what happens if it's a Lebesgue measure. Okay. So we put the following. So you have some function space with the probability, right? Which consists again of probability density functions with the property that every point the probability is positive, and that the integral of the probability over the entire domain is 1. So you have positive measure everywhere, which satisfies the normalization condition. So in this situation, so f is a function space consisting of positive L1 functions So if you recall, it's like there's a way to endow, it's like, function spaces with various sorts of norms. And in particular, it's like one of the very common norms are what are called LP norms, right? Where you sort of take the absolute value of the function, you raise it, it's like to the p power, you integrate it over the domain, and then you take the p root of that object. Okay, so the L1 norm, right, takes the absolute value of the function, raises it to the first power, integrates it, and then takes the 1th root of it. So that reduces to this because of the fact that p of x is greater than 0. So that really is, honest to goodness, the L1 norm of that probability density function. Okay, and in particular, it's like all these functions are positive, but they're also in this space of L1 functions. So we say a function is L1, I'm sorry, when its L1 norm is finite, right? And more generally, it's like you have an LP space if the LP norm, the P norm of that function is finite. Okay, so anyway, so this is F, right? Right, yeah. And then, as before, it's like, we want to talk about, the exponential families. It's like associated with this. So let's see what happens. So what we're trying to do here, it's like, just to put things in perspective, is that we're trying to use the intuition we've developed, it's like for discrete probability distributions, and we're trying to extend it in a natural way to this space of, it's like probability density functions on continuous random variables, right? And the way sort of to think about this is that with a discrete random variable, you have a discrete set of possible outcomes, it's like for the random variable, and associated with each of those points right, you have a certain probability distribution. Okay, so something similar happens in the continuous random variable case. You have a continuum, it's like of possibilities, and associated with each of those points, right, you assign a probability to it, with the proviso that, that probability changes in some sort of, it's like continuous way. It's like as you move along this random variable space. Okay, so now instead of just having again a finite number of possible outcomes, you have an infinite number of possible outcomes. So that's the sense in which this manifold, it's like a probability distributions, it's like defined on continuous random variables, is an infinite dimensional space. Okay, and we're just going to leverage, it's like what we know. It's like in again the discrete setting to the continuous setting in as obvious and possibly naive a way as possible, and see where that gets us. Okay, so now, for two probability distributions, so for two distributions, let's say P1 of x and P2 of x, right? There is an exponential family which connects those 2 points. It's given as follows. Okay, so P exponential of x, and there's this parametric dependence on t, right, is the exponential of the convex combination of the logs of the probability, as you might expect. Okay, so 1 minus t log P1 of x plus t log P2 of x. So the problem with just taking this combination of the logs, the convex combination of the logs of probabilities pointwise, and then exponentiating it, is that there's no guarantee that this object is normalized. So you have to add a normalization factor, which is this phi of t term. Okay. And yeah, so we have to, and then provided that exists in F, right? All right. Yeah. So, yes. So you still have to, I mean, it's like, so this would be fine. It's like so long as more or less it's like, I should say positive L1 functions here with unit norm, right? So this would be more or less fine as long as the L1 norm, it's like of the part which is obtained by just the convex combination of the logs of the probabilities pointwise, and then exponentiated, again without the normalization factor, gives you a sort of finite L1 norm, right? So so it could possibly be the case that, this thing blows up in L1 norm, in which case you can't deal with it with this normalization factor. Okay, so that's why there's this proviso that one assumes that it exists. It's like in this space. Okay, so a priori there's no reason to immediately expect that just because P1 and P2 it's like are in this space that this combination is necessarily in this space. Okay, all right. Anyhow, and so that's in some sense, the exponential geodesic. It's like connecting two probability distributions. In the same way, there should be a mixture geodesic connecting 2 points. So let's write it down. So the mixture family connecting them is given by P mix x t 1 minus t p1 of x plus t p2 of x. Okay, and then this is assumed to be in F. Okay, so right. So with this type of structure, it's like then again, it's like which again is in direct analogy to what we had in the space of discrete probability distributions, right? This is sort of the obvious analog of what we have before. Then, you can endow this sort of infinite dimensional manifold of probability distributions, right, with the structure of both a exponential family and a mixture family. Okay. So then F is regarded as an exponential and mixture family. Right, which is analogous to the case for discrete probability distributions. Which you recall is denoted by Sn, which is sort of the probability simplex. Okay. So the subtle issue here is this issue of topology. Which you endow F with. And topology is important because it talks. I guess the notion of what is in a neighborhood or something else. It's like whether in what sense it's like things converge, right? So topology, it's like which you endow. It's like function spaces. That's an important concept. And the point basically is that this family F, it's like of probability distributions that can be endowed with different types of topology, right? So in particular, it's like when you take the log of p versus p itself, it's like that induces different topologies. When you take different LP norms, it's like they induce different topologies as well, right? So L1 and L2 norms induce different topologies. Right, P of x versus log P of x induce different topologies. So this is the significance of this. Right, is to issues, sort of important issues or basic issues, like neighborhoods, convergence, sort of, and other things, right? So So in a sense, it's like when one does, for example, function analysis, right, which is sort of, in essence, the study of function spaces, one of the most fundamental issues is that one has to deal with, it's like time and time again, is how do you, what topologies you endow, it's like these function spaces with, it's like because they have an impact, it's like on, it's like the properties of that space. Okay, so anyway, so that's sort of an important caveat, which we're going to sweep under the rug. It's like for now, but at the back of your mind, you should always be aware that sort of issues like this, it's like do arise and are important. So, what's going to happen then in practice is that if at the back of your mind, it's like you're going to use information geometry in some sort of computational setting, right? You're going to try to compute something, you're going to try to figure out it's like what element of some, it's like say finite dimensional space, it's like of probability distributions, it's like you have a best fit, it's like to the data for, you're going to have to work with finite dimensional things, right? And so for example, it's like when you have a PDE, it's like you oftentimes construct a numerical method, it's like using choices of basis functions or shape functions. And so something similar is going to happen here. Okay, and so let's try to see what happens when you do that. So we're going to ignore sort of these sort of mathematical subtleties for now. And consider the discretization of say the real number line into n+1 intervals. Let's call them I0 to In. Then you can, given any probability distribution, it's like on that space, you can project onto some finite dimensional subspace of it the following way. So then the discretized version of P of x, right, is given by let's call that P, which is P0 to Pn, where Pi is given by just the integral over this ith interval of P of x dx. Okay, and then I goes from 0 to n. So one way to think about this then is that you've replaced this probability distribution by, in essence, I mean, there are many ways to think of it. One possible way to think about it is that you've replaced this, it's like probability distribution by a finite linear combination of characteristic functions, right? Sort of piecewise constant pieces, right? So if, for example, you had some sort of probability distribution like so, it's like in this setting, it's like what you might imagine doing is that you replace this curved piece by some piecewise flat piece, this by a piecewise flat piece, and this by a piecewise flat piece, right? And with the property that the sort of the integral of the probability density function with respect to whatever measure you've chosen over that interval is the same for the piecewise constant one versus the actual probability distribution. Okay, and it's like again, if you have some exposure to say the finite element method, then this idea shouldn't be too surprising. It's this one way of thinking about this is that this is like the degrees of freedom. It's like of a finite element method, or if you're thinking of it from the point of view of Fourier analysis, for example, it's like you have a function, you can replace that function by its Fourier series approximation, and then it's like what you do, it's like in order to figure out the Fourier coefficients is to take the function, multiply it by an appropriate dual test function integrated over the domain, right? And so you can think of this integral over the interval I sub I, right, as being something like taking p of x, multiplying it by a characteristic function, and integrating over the entire space. So here, the dual test functions, for lack of a better term, right, are the characteristic functions associated with I sub I. Okay, so hopefully it's like that sort of, drives home this message that, this type of finite dimensionalization, if you will, it's like of the space of it's like probability distributions. That's something which shows up again and again. It's like in sort of applied in computational mathematics. Okay, and so this is not really anything, different. It's like from that basic approach. Okay, so what happens then, as you might expect, is that because of the normalization property, and because of the fact that these intervals are sort of intersect only on a set of measures 0, and the union is the entire of R, this PIs is like, which form this P vector, is an element of the probability simplex. Okay, so this sort of gives a projection from F to Sn, and which approximates P of x, right, by P in Sn. Okay, and then conversely, if you will, right, if you want to think of it in the obvious way, you can have this P vector and you can map it to something which is just this linear combination of Pi divided by the norm of that interval times the characteristic function of that interval times x. I goes from 0 to n, right? So what this does is that given a element of the probability simplex, right, and these intervals I0 to In, I have an element of f, which comes from that. So, right. So, as I said, it's like what happens is that if you give me a probability distribution, I can project it. It's like into this probability simplex, and then once I have that, I can map it back. It's like to this sort of piecewise constant approximation of that probability distribution, right? So anyway, so you can do something, intuitively like that. Okay. Okay. So 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 you could imagine then that one way of dealing with f is to look at these projections onto the finite dimensional setting. It's like, and then let n go to infinity, right? So there is a sense in which p of x is regular enough. I'm not going to precisely specify what I mean by that. And sort of this set of intervals is chosen appropriately. So I'm going to hand wave repeatedly, right? And n goes to infinity, right? There is a sense in which this approximation sort of converges, right? And I mean, it's like usually the sense in which you want to talk about these things converging is in some sort of weak sense as opposed to a pointwise sense, right? It's like when you talk about probability distributions, what really matters is that it recovers the same probability, it's like, of something occurring for some sort of measurable subset of it's like of the reals. So imagine if there's some sort of interval, for example, in the reals. It's like, and you want to look at, well, what's the probability of the random variable being in that subset? You integrate, it's like p of x. It's like over that measurable set that gives you the probability. And then you want to do something similar. It's like to this kind of reconstructed object, which is the approximation, if you will, of that probability distribution. It's like if you integrate this object over that same measurable set, you want, these two things to converge to each other, right? And so that's the right notion of convergence, if you will. And the standard argument, more or less, is that again, it's like if this, it's like probability density function is somehow smooth enough, it's like regular enough, and you choose this sort of interval sort of in a good way, right? Then as the number of subintervals increases, goes to infinity, there's this sense, it's like of convergence, it's like of that probability distribution, in the sense of it recovering, it's like the probability of something happening, it's like in a particular measurable set, right? There's a sense in which that converges. Okay. So, and you can then imagine that that notion of convergence is like endows, it's like the original function space f, it's like with some sort of geometry, right? And this endows f with some geometry, right? Because if you recall this issue of geometry and topology, right, is going to affect issues like convergence and what have you. So the problem, it's like with sort of taking an approach like this in order to try to geometrize, it's like f, is that it depends on all the obvious things. It depends on how you've chosen this sort of sequence, it's like of intervals, it's like and what have you, in order to construct, it's like that approximating sequence. So this n equals n going to infinity limit, and sort of the geometry induces on f is not unique, okay? So this limit, so the geometry induced on f by the n equals n towards limiting to infinity limit depends on the discretization which you've chosen. Okay, so one has to be, again, careful about this. So again, it's like, let's try not to worry too much about that and then see where, this naive intuition takes us. Okay, so So let's just introduce a family of random variables. Delta s minus x indexed by this parameter, real parameter s. Which plays the role of the index I in the Kronecker delta function. It's like in Sn, right? So if we recall, it's like what's essentially happening is that you can write any probability density function for a discrete random variable as a formal linear combination of the Kronecker delta functions, right? So what's going to happen is that we're going to try to do the same thing now using the it's like Dirac delta function. You know, when we're doing this for probability distributions on continuous random variables. Okay. So p of x is going to be written as this integral from p of s ds. Sorry, p of s Dirac delta function s minus x ds. So if you recall, in going from finite dimensional to infinite dimensional, going from vectors to function spaces, right, vector spaces to function spaces, what happens is that instead of the sum over the index, you now have the integral over the index, right? So at the back of your mind, you should be thinking of this. So this is the continuous case, right? And then this is the discrete case, right? So this should be the sum over I equals 0 to n of pi, right? Dirac delta function like that. So here it's like I've summed over the i's. Here I've integrated over the s, right? So that's the analogy. Sum to integral, right? Sum over the index I, integrate over the index s, right? Kronecker delta versus Dirac delta, and then the probability distribution associated with that point or that index, right? So hopefully you'll see that this is entirely analogous once you squint at it sufficiently. Okay. All right. So the point then is that if you think of probability distribution written in this way, right, then this is a mixture family. Okay. And the other thing, of course, is that, you know, in order for this to be normalized, right, it has to have the property that this p of x sums up to 1, right? So the p sub I sums up to 1. And sort of this is analogous to the condition that the integral of p over the entire domain is 1, right? So there's again a normalization condition on the coefficients of the expansion, for lack of a better term. Okay? All right. So this shows that, that F is a mixture family. Generated by delta distributions, so Dirac delta. So delta is s minus x, right, where s is in the rails. And so again, this is in direct analogy to what we have, right? So, you know, it's like the PIs, it's like here, it's like in a discrete distribution are the probabilities associated. It's like each of the elements, it's like in the space of possible outcomes in the discrete random variable, right? So you want something analogous. It's like P at S. It's like for all possible S, where S again is all varies over all possible outcomes in the continuous random variable in question here. Okay, yes, and then the PS are of course the mixing coefficients. PS are the mixing coefficients. And there's a sort of clear sense in which this is essentially a convex combination of the Dirac delta functions, right? Okay, so all right, so this sort of allows us to think of this infinite dimensional manifold of probability distributions as a mixture family. So now let's see how we want to think of this as an exponential family. Okay, so I can also write this probability distribution as the exponential of the integral over theta of S delta S minus x dx minus this normalization factor, right, where theta of S is equal to log P of S plus the normalization factor, and this, which depends on theta of S, is the integral of the exponential of theta of S ds. All right. Okay, so now let's see what happens. So with that identification, we have that F is also an exponential family. Where the dot product we saw in the definition, it's like of the exponential family is generalized to this kind of functional space or function space inner product, if you will, right? So where theta, which is your affine coordinate, right, is equal to log of P of S plus this factor. This is the affine coordinate. And then you have eta of S is just P of S. So this is the dual affine coordinates. Then the dual convex function is given by following. So psi of eta of S is integral of eta S log psi of S log eta of S ds, right? Which is again sort of this negative entropy, basically. So you can check that its dual coordinates. Given by the following. So 8fs is the the expectation. It's like with respect to the probability measure p of the Dirac delta distribution, which is just p of s, right? And this can be expressed, it's like in terms of the Legendre transform of this sort of normalization factor, right? So gradient of phi evaluated at theta s. And one has to be a little bit careful about this. So this nabla is the Fréchet derivative. With respect to theta. And then we had already talked about the sort of the geodesic. It's like generated by in sort of the exponential family. It's like in the geodesic in the mixture family. So we've already discussed sort of geodesics, sort of the E geodesics and sort of M geodesics. Okay, in this setting. All right, and then we can look at the tangent vectors associated with that. Maybe let's just recall what these E and M geodesics are. So the E geodesic is given by P exponential xt is the exponential of the convex combination of the log of the probabilities. Right, and then the tangent vector to that is just ddt log p of xt L dot of x and t. So it's just log q of x minus log p of x. Okay. So here it's like I'm thinking of q as the second point instead of p1 and p2, but hopefully the idea is the same. Okay, and then the M geodesic, right? So if you call that sort of the mixture, so P mixture x and t is just this convex combination. It's like pointwise of the probability distributions, right? And then the associated tangent vector is just the difference of the probability distributions. So P dot of x and t is q of x minus p of x. And of course, it's like both of these things are obviously with respect to the appropriate E and M coordinate systems, right? Okay, Right, so let me just stop here for now, and then the next thing we'll talk about is the associated divergence functions to this space. But for now, let me just stop here.